Good day. This lesson is about divergence and curl of a vector field. Both are two important operations on vector fields in free space. These names originate in the study of fluid flow, in which case the divergence relates to the way in which fluid flows toward or away from a point, and the curl relates to the rotational properties of the fluid at a point. We will not investigate the physical interpretations of these operations, but we will focus only on their computation. Here are the objectives of this lesson. At the end of this lesson, you are expected to compute the divergence of a vector field and compute the curl of a vector field. We have here the definition of divergence and curl of a vector field. It says here, divergence measures the tendency of the fluid to collect or disperse at a point, and curl measures the tendency of the fluid to swirl around the point. Divergence is a scalar, that is a single number. Curl is a vector. The magnitude of the curl measures how much fluid is swirling. The direction indicates the axis around which it tends to swirl. The divergence of a vector field, we have F equals, in angle bracket form, f of xyz, g of xyz, and h of xyz, denoted by div f, is the scalar function defined by the dot product of del and f equal to partial derivative of the function f with respect to x plus the partial derivative of the function g with respect to y plus the partial derivative of the function h with respect to z. Take note that from the definition of the vector field a while ago in here, f is equal to the components of the three functions f, g, and h of x, y, z. Recall that if f is a function, the gradient of f is given by del f equals partial derivative of the function f with respect to x, partial derivative of the function f with respect to y, and partial derivative of the function f with respect to z. A useful mnemonic for this and for the divergence and curl, as it turns out, is to let del equals partial derivative with respect to x, partial derivative with respect to y, and partial derivative with respect to z. That is, we pretend that del is a vector with rather odd-looking entries. Recalling that you have the vector UVW times A is equal to UA, VA, and WA. So this is a scalar multiplication between a scalar number and a vector. Thus, we can think then of the gradient as del f is equal to partial derivative with respect to x, partial derivative of with respect to y, partial derivative with respect to z times f, which is equal to partial derivative of the function f with respect to x, partial derivative of f with respect to y, and partial derivative of the function f with respect to z. That is, we simply multiply the f into the vector. The divergence and curl can now be defined in terms of the same odd vector del by using the cross product and dot product. The divergence of a vector field f equals the vector component FGH is del.f equals, you have the component of your del to be partial derivative with respect to x, partial derivative with respect to y, and partial derivative with respect to z. Dot product with the component of f, which we have it as FGH, and performing the dot product, so we have here now equal to partial derivative of the function f with respect to x plus partial derivative of the function g with respect to y plus partial derivative of the function h with respect to z. For the curl of f is, we have the cross product of del and vector field f. And this forms a 3 by 3 matrix where we have the first row to be the vector ijk and the second row are the partial derivative of the function components with respect to x, with respect to y, and with respect to z. And the last row, we have the functions, which are the components of your vector field f, which are f, g, h. And if we're going to perform the basket method, so we can only add two columns rather in this matrix and performing the basket multiplication. Thus, we can come up with this formula, and that is now we have the first component for the curl of f is partial derivative of the function h with respect to y minus partial derivative of g with respect to z. Then the second component will be partial f with respect to z minus partial h with respect to x. Then the third component will be partial g with respect to x minus partial f with respect to y. So I would advise you not to memorize this formula because we can also employ, as I've mentioned, the basket method here, wherein we can copy the first two columns and then apply the basket method. We must observe that the divergence of a vector field f and the curl of f rather, depend on the point at which they are computed, and hence are more properly written as div f of xyz and curl f of xyz. However, even though these functions are expressed in terms of x, y, and z, it can be proved that their values at a fixed point depend only on the point and not on the coordinate system selected. This is important applications since it allows physicists and engineers to compute the curl and divergence in any convenient coordinate system.